So let's now turn to the problem of finding common subwords and subsequences between two sequences. So the first problem we look at is what's called the longest common subword problem. So let's suppose we are given two words. For the moment, let's just assume they're words in English or a language like that. We are given two strings and we want to find the length of the longest common subword between them. And a subword is just a segment. Right? So for instance, if I have secret and secretary, then the longest common subword is just the prefix secret, okay, and it has length 6. Between bisect and trisect, I have this common segment isect. Okay, if I have bisect and secret on the other hand, then the common subword is of length 3, namely sec. And if I have director and secretary, then there are actually only two length subwords and there are two of them. So EC occurs in both of them. Okay? And so does RE. Okay? So we may have more than one candidate for the longest common subword. But our main goal at the moment is to compute not the subword itself but the length. We will see how we can recover the subword quite easily from the length calculation. So the focus at the moment is to get the length of the subword. So let us look at this thing more formally. Okay. So we have two words A0 to AM and B0 to BN. Okay. And now what we want to say is that if I write out A0, A1, then I have a position AI, AI plus 1 and so on, and then AM. So if I can find some segments starting with AI and BJ, okay, such that if I start from here and I read off K letters, if I start from BJ and I read off K letters, so I read AI plus 1 or to K minus 1, I plus K minus 1, and BJ plus 1 or to BJ plus K minus 1. Then if these are both K length segments which are equal, then I will say that U and V have a common subword of length K. So they must be a matching segment of the word. And now the aim is to find the length of the longest such segment. So the longest common subword of U and W. So here is a brute force algorithm, right? You just try out every position. We look at every AI and BJ, right? So you look at every I and J, I between 0 and M and J between 0 and N. And then I just keep looking, right? I look at the next, if these two match, I look at the next letter and go on. I keep going until I find two positions which don't match, right? Then I know that the longest subword starting from these two positions is only this much. Right? So I match AI, BI, AI plus 1, BI plus 1 as far as possible and I keep track of the longest such match. I do this for every AI and BJ. Okay? So if M is greater than N, then first of all, the number of choices of AI and BJ is M times N. And in general, I will go to the length of the end of the shorter word matching everything. So I could do order N work before I reach the end of the scan. Okay. If everything matches until the end of the shorter word, then I could do order N work. Okay. So therefore, this will be O of M times N into N or O Mn squared. Right? So now our goal is to see whether we can make this more efficient by doing something inductive on this. So the first observation, the inductive observation is that if I have AI plus 1, if I have BJ plus 1. Okay. So if I have a subword starting from here of length K, then if I look at the next position and go forward, this must be a subword of length K minus 1. Right? So there is a common subword of length K at ij, if and only if there is a long common subword of length K minus 1 at I plus 1, J plus 1. So in other words, I look at ij. If ij is equal, okay, then there is possible to start a word at common subword at AI and BJ. So if AI is equal to BJ, I look at the longest common subword I could have got from I plus 1, J plus 1 and add 1 to it. On the other hand, if AI is not equal to BJ, then I cannot have a common subword starting here because the very first letter doesn't match. So then I just say the length of the longest common subword starting at that position is 0. So this gives us a handle on the inductive structure. So I look at two positions. If they are not equal, I declare that there is no common subword starting there. If they are equal, then I postpone the problem to the next position and add 1 to whatever I get in the next position. And the boundary condition is when one of the words is empty, right? When we have no letters left, so we can't extend one of the words anymore, we can't go forward, then we can say that there cannot be a common subword because there are no letters to use from one of the two words. Okay. So for convenience, although our words go from A0 to AM and from B0 to BN, okay, we will allow an m plus 1th position and an n plus 1th position. So we'll have positions 0 to m plus 1 in U and 0 to n plus 1 in V. So m plus 1 means I have gone beyond the last position in U, I have exhausted all the letters. Likewise, n plus 1 in V means we have reached the end of the word in V. So what we said is that if we have reached the end of the word in U, then no matter where we are in V, there is no common subword. So the length of the common subword is 0. Likewise, if we have reached the end of the word in V, wherever we are in U, there is no common subword, length is 0. And if we are not in these two cases, we are not at the end of the word, then we check whether AI is equal to BJ. If AI is not equal to BJ, we declare, as we saw earlier, that the longest common subword has length 0. Otherwise, we inductively compute the value from the next position in both the words and add 1 to it, because we can extend that word by 1 because AI is equal to BJ. So we could write a memoized recursive function for that, but we will directly try to compute a dynamic programming solution for this problem. Okay. So we will typically have these sub problems of the form LCW IJ. Right? These are our basic sub problems. So what we saw from the earlier thing is that if I have AI equal to BJ, I need to look at AI plus 1, BJ plus 1. So LCW IJ depends on LCW I plus 1, J plus 1. Right? So we have this kind of sub problem dependency. At every point, a value needs to look to the one which is below. So we have in this, just to be clear, this is our I and this is our J. Right? So it has to look down and right. So therefore, with our convention that we draw the arrows backwards, that is, if this square depends on this square, then we draw an arrow indicating the dependency in reverse. Right? So I need to compute the bottom of the arrow before I can get to the top of the arrow. That's what the arrow says. I need to compute this before I can compute this. Okay? So now we can start at this corner because this depends on nothing and then start working. So as we saw at the boundary where I have exhausted one word, where either the first word or the second word is, so we have written the word, by the way, bisect and secret, just to tell us what the values of AI and BJ are. So these are the values of AI and these are the values of BJ. Right? So these are my two words. So initially at the boundary, every longest common subword is 0 because one of the two words is empty. And now I can do it, say, row by row or column by column. So let's do it by column for a change. Okay. So now at this point we have that A5 is equal to B5. Therefore we get 1 plus LCW of 6, 6. Right? And therefore we get a 1. Everywhere else, C and T, E and T, there are no other T. So everywhere else it is just 0 because the value don't match. Now if I go to the previous column now, here the only one that has anything to say is E and E, but there because the next one was 0, I just get 1 plus 0 is 1. If I go to the previous one, in fact the value, no, there's no R in bisect, so therefore all the values, the subword is 0. If I come to the next thing, again now I have one place where C and C match, so I say that the longest common subword starting here is 1 plus whatever happens at T and R, but T and R don't match, so it's 1 plus 0 is 1. But now because this C is now preceded by an E, so at this E I find that it is 1 plus whatever happens to the bottom right, so it's 1 plus 1 is 2. And likewise at S I find that S and S match and it is 1 plus whatever is to bottom right, so it becomes 3. Right? So we identify in this way, we put an entry 3 here. So in this particular table it's a bit mysterious where the answer is. Okay? So what we have to do is find the entry with the largest, find the entry which has the largest value. In this case 2, 0, this is our largest value. Okay, so this tells us that between these two words the longest common subword has length 3. As I said before, we are only computing the longest common subword, so how do we actually find the subword? Well, we can actually, in this case, very easily read it off. We know that there is the longest common subword here of length 3. That means that it must be succeeded by a word of length 2 and so on. So this particular diagonal tells us what the letters in the word are. And if I just project this diagonal onto both the one column, I'll get the word SEC. Right? So in this example, as we see, once we've computed the length, it's very easy to read off the solution. So here is some code for this particular algorithm, the dynamic programming version. Just to make it less confusing, I have explicitly used the variables R and C instead of I and J. So R is the row, it goes this way, and C goes this way. Right? So what we say is that initially, if I am looking at the last column, okay, these are all zeros, okay, and if I am looking at the bottom row, right, this empty. So remember that the numbering is from 0 to n plus 1 and from 0 to n plus 1. So if I'm looking at the bottom row, when the row number is n plus 1, every column is 0. So this puts the zeros. So these two lines just populate the things. Now we have to find, remember the goal is to find the maximum position in the entire array in order to give the answer finally. So we'll just keep track of that with the value here. So we'll initially assume that the maximum common word is of length 0. Now what we do is we just go column by column, row by row, right? So we go for each column from n to 0. So we do column by column, and each column we go row by row from bottom to top, m to 0. Okay. We look at the word position R and position C. Is UR equal to BC? If so, I add 1. So this should be W by the way, not S. So if I have U of R is equal to B of C, then the longest common word, length of the longest common word RC is 1 plus at R plus 1 C plus 1. Otherwise it is 0 because there is no common word. And if the new value I have computed is bigger than the value I have seen so far, okay, then I will update it to the current value. And finally, at the end, I will just return this length. Okay, so it's a very straightforward, iterative way to process this thing column by column. You could invert these two indices and do it row by row. Okay, so that is an exercise. So we had seen earlier that if we just look blindly at every position and try to scan the word starting at that position, we get something which is of order mn square. Now this solution requires us to fill in the table of size m times n. So obviously every entry in this m times n table, we just have to look at the neighbors to fill it up. So it's a constant time operation. So m times n entries, we fill in m times n times, so we have an order m1 n algorithm. If you use dynamic programming, we have done it. But if you use memoization also, you will get the same answer. Although remember that the recursive calls might cost you in terms of actual implementation time. So we can now look at a slightly more general problem than longest common subword, and one which is more interesting computationally. So what if we don't look for an exact match, but we allow ourselves to drop some letters? Okay. So we have a subsequence, not a subword, which allows us to drop some letters, and now we want to know if after dropping some letters, what is the longest match we can find. So in our earlier examples, some of them are the same. Like in this case, without dropping any letters, I could get 6 and I can't improve it. Same way with this isect, I cannot improve it. But now if I look at bisect and secret, earlier we only had a length 3 match, SEC, SEC. But now I can extend this match to length 4 because here if I add a T, here I can drop 2 letters and get a T. Right? So I can actually get a match which is length 4. Likewise, in these two were director and secretary. Earlier we had RE, RE, and we had EC, EC. Okay, but now by doing this dropping, I can get ECTR and I can get ECTR, right? And similarly, I can get RETR and I can get RETR. Okay, so if we allow ourselves to drop letters, we can get longer sequences that match. And this is called the longest common subsequence. So one way of thinking about it in terms of our earlier longest common subword is that I can now, if I have matched a certain segment, I can continue to match to the right. So I can let both indices go forward. So I can go down and right in the grid and look for another place where there is a match. So earlier we had a 3-level match between SCC and then we had a 1-level match between T. So I can combine these to make a 4-level longest common subsequence. But we will do the subsequence calculation in a much more direct way than this. So before we proceed, it's useful to look at why the longest common subsequence problem is interesting. So one of the areas is in bioinformatics. So biologists are interested in identifying how close two species are to each other in the genetic sense. So if we look at our DNA is basically a long string over an alphabet of size 4. Okay? So these are 4 proteins that form our DNA. They are abbreviated as ATGC. So now if we look at 2 strings of DNA, a natural way to compare how close they are to each other is to ask how well they can be aligned if we just drop a few things here and there. Right? So it could be that one species has a few extra genes, another species has a few extra genes doing something else, and if you drop those genes, then everything else is the same. But these genes may occur at different places in the 2 species. So it's not that there is a common part and then there is an extra part. It's rather that the new genes are interspersed among the other genes. So we need to know if we can drop a few genes in one and a few genes in another, can we overlap them? So that's the longest common subsequence problem. If you use Unix or Linux or any related operating system, there is a command called diff which allows you to check whether 2 text files are the same or find a minimal difference between them. So the diff command also does a longest common subsequence. It treats each line as a character and it says what is the minimum number of lines I can drop between these 2 files before I can match them up, and then it tells you how to insert things back. But basically it's doing a longest common subsequence calculation to tell you how close 2 text files are to each other. So there are plenty of applications for this longest common subsequence problem. So let's try to understand the inductive structure of this longest common subsequence problem directly, not through the longest common subword. So the first thing to note is that if I'm looking for this longest common subword between 2, and supposing I find that A0 is in fact equal to B0. Now I claim that I should combine them in the solution and then look for a solution in the rest. Okay? So I should do something where I say that there is one match A0 equal to B0 and then I must find the rest. Okay? So this requires a little bit of an argument because it could be that this is not the optimum way to do it. Right? So remember, this is a bit like a greedy thing. We are saying that because A0 is equal to B0, match it up and then proceed. So one might argue that this is not the way I want to go. Supposing A0 in fact should be matched to B2. Okay, that would be the best solution. So it is not a good idea to match A0 to B0. But now notice that if A0 is matched to B2, because it's a subsequence, then anything to the right, say A1 is matched to something, it must be further to the right? These lines, I cannot have anything which crosses like this. I cannot have any match with crosses because they must occur in the same sequence. So if A0 is matched to B2, A1 must be matched to something to the right. A2 must be matched to something still further to the right and so on. Right? So all these matches go from the top word to the bottom word without crossing each other. So now if I take this solution and I know that A0 is B0, then I can actually move this arrow here and make it match like this and remove this. What will this do? It will disturb the original solution by no longer saying A0 is matched to B2 but A0 is matched to B0. But in terms of the quality of the solution, right, the number of matches is the same. Earlier A0 was matched somewhere else, now it is matched to B0. So the length of the longest common subsequence does not change. Right? So turning this argument backwards, it says that therefore if A0 is equal to B0, it is very safe to assume that A0, B0 forms part of the solution and proceed with the rest of the problem. So we can look at the sub problem from A1 and B1. Right? So this is the first case. So the first case says that we can look at, if A0 is equal to B0, we can look at this sub problem from A1 to B1. Now, if it is not equal, okay, then one is not sure what to do. It's not a sound idea to drop both. Okay? For instance, supposing I have something like straw and a stray. Okay? Then just because the S doesn't match the A, it doesn't mean that I should remove both of these, because I should keep the S alive to match with the next S. Right? So both cannot be there because they don't equal each other. And if S matches something on the right, then A cannot match something, because if they are both different, right, if they are not equal, then this must match something there and this must match something here, and both cannot happen because they will cross, and this we said is not allowed. So only one of them can match something to the right on the other word, but we don't know which one. So this is what the general principle of these inductive solutions is, that you don't try to choose one or the other, right? So if I leave B0 and I drop A0, then I get a solution, I get a subproblem which has A1 to AM and B0 to BN. If on the other hand I keep A0 and I drop B0, then A0 to AM remains, but now it's B1 to BN. Okay? So these are my two possible subproblems, knowing that both A0 and B0 cannot be there, but I should allow one of them to be there, otherwise I might have a suboptimal solution. So dropping one of them, it's like in the job scheduling case where you say that if this job is there, something else is not there. Right? If A0 is there, B0 is not there. If B0 is there, A0 is not there, but beyond that I can't say anything. So therefore I solve both of these problems in principle and take the maximum, the better of the two. Okay, so this is the inductive structure now. Either the first letter matches, in which case I include it in my sequence and solve the remaining subproblem, or the first letter doesn't match, in which case I generate two subproblems, one by dropping each of the letters in turn, and I take the maximum of the two. So as usual, let LCS I comma j stand for the LCS of the problem starting at AI and BJ. So if AI is equal to BJ, as we said, LCS of ij is 1 plus LCS of I plus 1 j plus 1. This says we will assume that AI equal to BJ is included in our solution and then proceed with the rest of the input. If it is not, then I have to drop one of them. So either I look at LCS I plus 1 comma j or LCS ij plus 1. I look at both and then I take the maximum of these two. And there is no other thing because the current one doesn't match. So as with the longest common subword problem, we will extend the positions to go beyond the word to indicate the word is over. So we will go from 0 to m plus 1 and 0 to n plus 1. And when we have reached m plus 1 or n plus 1, then the LCS problem will give us 0 because there cannot be a common subsequence since one of the words is going to be empty. So the subproblem dependency in LCS is a little more complicated than in LCW. In LCW, we only had this dependency. That is, we said that ij depended on I plus 1 j plus 1. But now we have also a dependency on I plus 1 j and ij plus 1, right? So we have a dependency coming from the right and from below as well. So we have a three-way dependency. As we saw, all these values are going to be 0 here, right? So this is the first non-trivial value that we can compute because all its three neighbors are known. Nowhere else are all. So if you look at here, for example, the bottom neighbor is not known. If I look here, the right neighbor is not known, right? So at LCS m comma n, 5 comma 5 in this case, the value is available to compute because everything around it, the three dependent squares around it are all populated. So I can do that and then I can again do row by row. Once I've got this, I can do this because I'll have all three values. Once I do this, I can go left, I can do this and so on, right? Or you can do diagonally. So let's do it column by column, right? So we start with the base case where the LCS at the boundary is 0 because you cannot have a longest common subsequence with an empty word. Then we fill up the first column and here we get a 1 because when the two match we have 1 plus LCS of I plus 1 j plus 1. Right? Now we have some differences. So when it doesn't match, like when C, so if I look at C and E, they don't match, then what I'm supposed to do is I'm supposed to take the maximum of these two. So since I take the maximum of these two, I get 1. Now since I take the maximum of these two, I get a 1. Maximum of these two, I get a 1 and so on. So the longest common subword problem, it said if the current letter doesn't match, then I get a 0. Here it's not there because I'm allowed to drop this letter and go ahead, right? So therefore this 1 propagates along this column. Similarly, the 1 propagates along the previous column because nothing is an R. Now I get some additions. Okay, when I reach C and C, it is 1 plus I plus 1 j plus 1, so I get a 2. Likewise, when I go to the next column, when I reach E and E, it is 1 plus I plus 1 j plus 1, so I get a 3. And finally, when I reach this S and S, okay, I get this 4, and now this 4 propagates because here I take the max of these two, so I get this 4. Max of these two, I get 4. So in this particular case, actually LCS of 0, comma 0 is my answer. Remember in LCW I had to look around in the whole grid to find out where the maximum was. In LCS you don't have to do that. The value you get at 0, comma 0 is actually the answer you're looking for. Okay? And now as before, you can trace back the path. Why was each value filled? Was it filled because it is 1 plus I plus 1 j plus 1, or was it filled because it was max of the other two neighbors? If so, which was the max? Right? So it's very clear that this 4 came because it was a max, because s is not equal to b, so it came from below. And this 4 also came from below. Now s is equal to s, so this came from here, and so on. So you can trace out this value, and everywhere where you have this diagonal, okay, it was there because the values matched. So the value is 4, and there are exactly 4 diagonal steps. This one, this one, this one, and the one on the bottom right. Okay? These are the 4 matches which constitute the longest common subsequence, and you can read it off by the thing, and it forms the sequence SCCT. Okay? So as we saw before, provided you can compute the answer numerically, you can go back and retrace that computation and figure out the witness, as it's called. Which word actually, which subsequence actually gives rise to this answer. So the code for LCS is a little bit simpler than for LCW, because we don't have to keep track of this maximum value and where it occurs, because we only need to find the value at 0, 0. So as before, we use R and C to be a little clearer, that rows goes this way and columns go this way. So columns go from 0 to n minus 1, n plus 1, and rows go from 0 to n plus 1. So we initialize the boundary to be 0, and then we do column by column, row by row from bottom to top. If the two are equal, then you add 1 plus the value of the bottom right. If the two are not equal, I take the maximum of these two values and copy it. And finally, when those values are filled out, I return the value at 0, comma 0. So this is similar to LCW. Right? We basically fill out an n size table. Each entry in the table is easy to compute. It takes only a constant amount of time. You have to look at the 3 neighbors. And therefore, overall, using dynamic programming, we have demonstrated an order mn algorithm. You can also use memoization at the cost of recursion.